Hello everyone. Today I'd like to do some sample problems with Newton's third law and the system approach. So we'll try the first one. It's more of a conceptual type problem. A train engine pulls 3 carts of unequal mass. Which link would have the greatest tension? So in this particular case, we're told to neglect drag. So we don't have that resistive force against this train cart. We have 3 links, A, B, and C. And we want to look at this case of both constant speed and speeding up. So if you want to pause the video and try to answer these on your own, you can. And in a second here, I'll go over it with you. All right, so looking at the first example with constant speed, in order to be at constant speed, then we need all of the forces to be in equilibrium. So if I were to do a free body diagram for each of the train cars, the 3M, the 2M, and the M, if I were to try to include the tension in these lengths, in order to keep it at a constant speed, I need all those forces to be canceling out. So maybe if I started with just the 1M, I would be tempted to say that this free body diagram would be something like this, where we have the force of gravity of little m, there is a normal force keeping it from falling, and then I might say a tension to the right, let's call that F tension A, and then maybe a tension to the left, F tension B. And I'm trying to be clever here, making the tensions equal in magnitude in order to make sure that little m is in equilibrium so that they could be traveling at a constant speed. So the first thing I'm going to say here is that those tensions would need to be equal in order for them to be in equilibrium. And then the same thing would happen for the 2m. I would need the tension in B to equal the tension in C. So I'm convinced at this point that the tensions need to be equal. But when I go to do the free body diagram of the 3m, things get a little bit more interesting. That's Fg of 3m, and that's then the normal force on 3m, and my vertical forces are in equilibrium. They're canceling out because they're equal in magnitude. If I were to try to put a tension here for link C to the right, the question is, how would you put 3m in equilibrium? Well, you would need a force to the left that's canceling out that tension from link C. And because we're told to neglect drag here, there really is no leftward force. And if there's no leftward force, in order for 3m to be in equilibrium, it actually means that the tension in link C has to be 0. And as I consider the other free body diagrams for both the 2m and the m, if the tension in link C is 0, then the tension in link B has to be 0 to keep the 2m in equilibrium. And if the tension in link B is 0, then the tension in link A would have to be 0 to keep the m in equilibrium. So not only are they equal, but they're actually equal to 0. So each of the tensions need to be 0 for this object to remain at a constant speed. Now, it does get more interesting if we want the object to speed up. So as this train is moving to the right, so our direction of motion is that way. So I'll just say our velocity is to the right. Now when I draw those free body diagrams, I need the rightward force to win. So for example, if I'm looking at little m, and I've got Fg little m and Fn little m, then I need the tension in link A to be greater than the tension in link B. So the first thing I can say is that the tension in A is greater than the tension in B. And for similar reasons, when I do the free body diagram of 2m, I can show that the tension in link B has to be greater than the tension in link C, so that 2m can also accelerate to the right. So we have A, B, and then C. Now, I could also use the system approach to prove this as well. If I'm looking at each of these links, and I could say, okay, what is link C responsible for pulling along? Well, link C is only responsible for pulling along 3m. Now, all of these objects are moving at the same speed with the same acceleration, so I could take the system approach, and I could put the 3m and the 2m together, and I could treat them like a 5m object. and I could ask, what is link B responsible for pulling along? Where in this system, link C is an internal third law pair. It pulls backwards on the 2m, it pulls forwards on the 3m. So that would cancel out when I look at the total system of 5m. So if I look at link B specifically, I can say that link B is responsible for pulling along a 5m at the same acceleration as everybody else. So if B has to pull 5m and C only has to pull 3m, then we could show that B must have a stronger tension because it's pulling more mass. And similarly, if we extend this system and draw a box around all of our train carts and consider that to be a 6m object, and now B and C are internal third law pairs that would cancel out, I can say that A, link A, is responsible for pulling along 6m. So it's pulling the most mass with the same acceleration as everybody else, so then the tension in link A has to be the greatest, and the tension in, my apologies here, link C is the least. So A is pulling the most mass, B is pulling 5m, and C only has to pull along the 3m. Okay, so that was more of a conceptual. I would like to get to a quantitative type problem. I have here an Atwood's machine, which is just a series of pulleys and different masses, and they are released from rest. So V initial is 0. And we are assuming here that these are ideal pulleys, meaning they don't offer any friction or any additional inertia. So it's just the larger mass is going to drive this motion. So we're given a series of different pairs of masses. In every case, big M is larger than little m. So in every one of our examples here, little m is going to be moving upward, while big M is going to be moving downward. The reason that we have pulleys is just to change the direction of the force from the string. So pulleys have the ability to change the direction of the force. What I should do in each case of a dynamics problem, I should draw a free body diagram. So I will start with big M. Big M is going to accelerate downward because it's the heavier mass. So I'll draw the force of gravity on big M larger than the force of tension in this string. So then I have Ft upward. Now, that same string carries the force along. The direction of that force is changed by each of these pulleys, but it's the exact same string that's pulling on little m. So I want to transfer that same tension and this series of third law pairs as each fiber of the rope pulls on the next. That exact same tension that's happening on big M is also pulling up on little m. So that is, after a series of third law pairs, those two tensions are equal in magnitude. And I also know that little m is going to accelerate upward, so when I draw the force of gravity on little m, I'll make sure that I draw it smaller than the force of tension. Now, what I'd like to do is go through and color code each of these forces. If they're in the direction that the mass moves, I'll color them green. So my tension on little m is going to be green, and my weight of big M is going to be green. And my tension on big M is going to be red because it's against the direction that it moves, and my tension on little m, or sorry, my force of gravity on little m is going to be red because it also is against the motion. Now, the system approach allows me to sum all of the forces that are acting on these objects, and I can treat them as a system because as long as the rope is tight, they will move with the same velocity and same acceleration. So if I were to add all of my forces, I'll always start with the largest. What I'm really finding here is the magnitude of the net force. So I will start with the largest force, the one that I know is going to win and drive the motion, and that is the force of gravity on big M. And then I'll just move backwards along the direction of motion. So I have a tension that is against the motion of the objects. Then I have a tension that is in the direction that the objects move. And then I have the force of gravity on little m. So that is in red. And that is the sum of all of my forces, or the net force. And that should be equal to, according to Newton's second law, that should equal the total mass times acceleration. So I have big M plus little m. And as we showed in the last video, when you have an internal third law pair, these tensions are going to cancel out. One is in the direction of motion, one is against the direction of motion. So really the net force on the system is just the weight of big M minus the weight of little m. And that should equal the sum of the masses times acceleration. So I can then find the acceleration of the system by subtracting the weights, Fg of big M minus Fg of little m, divided by the sum of the masses. And that should give me the acceleration. So remember, to find the weights, I'll do mass times gravity, or gravitational acceleration on Earth, minus the weight of little m divided by m plus m. So my acceleration should be, for the first example, where the mass of big M is 8 kilogram and the mass of little m is 3 kilogram, I have 8 times 10 minus 3 times 10, or 80 minus 30, divided by 8 plus 3. So I have 80 minus 30 divided by 11, 80 minus 30 divided by 11, and I'm coming up with about 4.55 meter per second squared. Okay, so that's just one combination of masses, 4.55 meter per second squared. If you'd like at home to pause the video and try the other three combinations using that same method of the system approach, go ahead and try that now. Okay, and then if you work through those, the answers we should be getting here are about 2.31 for the 8 and 5 combination, 0.67 or 2/3 for the 8-7 combination, and 1.76. Okay, so we are using that internal third law pair. We know that it cancels out because they're equal and opposite, and we are summing all of the forces in our system to get the net force on the system. Okay? If we were asked to go in and find the tension, if we actually needed to know the tension in the rope, because what might happen is we could have a qualifier type question where it says if the tension gets over 10 newtons, the string is going to break. And all the while, we're treating it like a system, acting as if these masses are going to stay together. But if the tension exceeds 10 newtons, then the rope breaks and both the masses fall. So if we need to find the tension in the strings, what we can do is go back to our individual free body diagrams, and we can sum the forces on those individual masses. So if I were finding tension in this case, I have two choices. I could look at the free body diagram and the net force on big M, or I could look at the free body diagram and the net force on little m. I personally would choose little m because tension is in the direction that little m moves. And that means that tension is the larger force. So that's what I'm going to do in this example. I'm going to use the free body diagram on little m, and I'm going to sum the forces of little m. So if I were summing the forces on little m, I would say that tension is greater than the weight of little m. So I would subtract the weight of little m from the tension to get the magnitude of the net force. And that would be equal, well, if I'm only looking at little m's free body diagram, I'm not adding the masses together anymore. This is the net force on little m. So the sum of the forces should equal little ma. And I want to get the tension by itself, so I would add Fg of little m to the other side. So in my opinion, that makes the algebra a little bit easier to do this with little m. If I were doing it with big M, then I would have written the sum of the forces as weight of big M minus tension. And I just wouldn't want to deal with that minus in front of tension. It just makes the algebra slightly more complicated. But you could definitely do that if you wanted. So at this point, in order to find the tension in the string, I would do little m times the acceleration plus the weight of little m, which would be little m times g. Now I'll just do this for the first scenario. I'll determine what the tension was. We know little m had a mass of 3, and the acceleration was 4.55. So I have 3 times 4.55 plus 3 times the acceleration due to gravity on Earth, which is 10. So I have 3 times 4.55 plus 3 times 10 and I'm coming up with about 43.65 newtons. So the tension in the string is 43.65. If this were a qualifier type problem, if they said the string breaks after 10 newtons, then we'd have a problem here. We have treated it like a system. We've said that they stuck together, but we now realize that if they stuck together, the tension would have exceeded that qualifier. But in this case, we're just looking for that value. Let's say that the string doesn't break. If it stayed together as a system, the tension in our string would be 43.65 newtons. Okay? So I hope that is enough for you to get through this week's problems. If you have any questions, let me know. And thanks for watching.